Water is pumped at a constant rate of 10 cubic meters per hour from an open tank on the floor to an open tank with a level that is 10 meters above the floor. Frictional losses in the 50 millimeter diameter pipe between the tanks are at 3.5 joules per kilogram. At what height above the floor must the water level be kept in our supply tank if the pump can develop only 0.1 kilowatts, or about 100 watts? The pump is 75% efficient. Alright, so we got a schematic, we got a supply tank, a receiving tank, and a pump in between. There's a bit of an elevation difference, and notice this is not a very powerful pump. We are flowing water. This is a pretty, so a 5 centimeter diameter pipe, a couple inches in diameter. We want to know what height this level must be so that we can get water flowing through here. This pump is not very powerful, 100 watts, and it's only 75% efficient. So only 75 watts of power are actually being delivered to the fluid. That's not a whole lot of energy, and we're trying to fill it, ramp it up to 10 meters in elevation from the floor. So what we're going to have, is we're going to have, if you want to think about this somewhat qualitatively, is we're going to have the static pressure here contribute to pushing this fluid through the system up to that height. What's going to happen is if this level at position 1 were to go down far enough, the pump would no longer be able to push liquid in. And if something were to happen and this level were to rise, we would actually start to get fluid flowing backwards if there were no kind of checks to that happening. But once it reaches a certain level, then there's going to be nothing moving, and we'll probably burn our pump motor out. So anyway, the way I like to start these problems, number one, we've got our schematic. We've got our positions where we're going to apply a Bernoulli equation balance. And so what I like to do is write the overall Bernoulli equation, the general Bernoulli equation, and then start thinking how we can simplify these terms. So my reference, I am going to set my reference at the floor. So everything is going to stay positive, and so Z2 is going to equal 10 meters. Z1, that's our unknown. That's our unknown. So that's what we're going to be solving for. Both tanks are open to the atmosphere. So P1 is equal to P2. These pressure head terms are going to go away. They're going to cancel each other. Right? What about the velocity head terms? Well, we're dealing with tanks. The levels in these tanks are going to stay constant. So the velocity of the fluid at position 1 is essentially 0. The velocity of position 2 is essentially 0. So these velocity head terms are going to cancel out. Do we have head being added to our system? Yes, head is being added to our system by the pump. And we're told what the pump power is, so we'll be able to do that calculation. Any head extracted? Nope, no head extracted. What about head loss? Yes, we do have frictional losses in the piping. We do not know anything that much detail about the piping, but we are told what the frictional losses are. But note that the units are a little strange. The units are energy per mass. We are not used to dealing with that. This Bernoulli equation is not written on an energy per mass basis. It's written on an energy per weight or head basis. So what we're going to have to do is we're going to have to take this head loss term and we're going to have to convert that to energy per weight. And of course, we've got steady state flow. I should have mentioned this at the beginning, and the water is incompressible. So once we make these simplifying assumptions to the Bernoulli equation, you get a relatively simple equation out of it. And so here what we're doing is we're solving. Here we just have terms crossed out, and then here in this form we've got the Bernoulli equation solved for Z1. And so notice we know what Z2 is, that's 10 meters. The head loss term, that's 3.5 joules per kilogram. We're going to have to convert that to head. And then head added. What is head added? That's the power supplied, that's energy per weight supplied by the pump. Well, that is given in horsepower, or sorry, watts or kilowatts. And so basically what this comes down to is a unit conversion or dimensional analysis once we apply our simplifying assumptions. So that all is captured here. Let's look first at the head loss term. It's given as energy per mass. How do you convert mass to weight? You take the mass and you multiply it by the acceleration. In this case, it's acceleration due to gravity, and so we multiply by 1 over g, or we divide by g. And so our head loss in terms of weight is just head loss mass divided by g. Again, MathCAD, g is an inherent variable, 9.81 meters per second squared, and notice we do that, we get head loss of 0.357 meters. Remember, that's also the same as joules per Newton. Another thing we can do, and I went ahead and did this calculation, I was kind of curious to see how much of this pump's power is going to overcoming these the frictional forces. So we can do this. We can take the head loss and we can multiply it by rho g times the volumetric flow rate. We're given all that information, and we can see that of the 100 watts total, but 75 watts actually being applied to the liquid, 9.77 watts, or 9.72 watts of that goes to overcoming the frictional losses. So now all we have to do is worry about the head added term, and for that what we can do is just remember, you do the same kind of calculation we did here. The power actually added to the fluid is the pump rating times the efficiency. So that's going to be 75 watts, and then we convert that to head. And so we take the power added, 75 watts, divided by rho GQ. Look in your notes for the derivation of that. It's pretty straightforward. And we get the head added term is 2.753 meters. Now we can simply plug these numbers in and solve for Z1. Z1 is equal to 7.6 meters. So what that means, go back to our schematic, as long as this liquid level is 7.61 meters, we will get flow through the system. If this liquid level drops below that, or at this level, there will be no flow. All right, there will be no flow, and we'll probably burn our pump motor out pretty quickly. If this level were to drop below that for some reason, then you would get backflow. So this problem is it's a relatively simple problem. No horrendous details in the piping because those head losses were given to us. A lot of this was an exercise in understanding how the units and dimensional analysis work in these process fluidic questions.